A triangle can have 3 right angles, and every corner is genuinely square on the surface beneath it. The familiar 180-degree rule is correct on a flat plane, so place that flat triangle beside the globe. The disagreement is not an arithmetic trick. It exposes one hidden assumption inside the rule. The space containing the triangle is flat. Rotate the globe toward the North Pole. The 2 meridians become perpendicular radii, and the hidden third square comes into view. Now the count is unavoidable. 90 plus 90 plus 90 equals 270 degrees, with no distorted corner and no unfair side. The real question is no longer whether this works. It is what changed underneath the triangle, and how the triangle can measure it. Restart with a traveler at the North Pole. The destination is hidden, but every allowed step must remain on the sphere. Trace due south along 1 meridian. This path is 1/4 of a great circle, not a line drawn through the globe. Extend that meridian around the hidden side. Its completed circle cuts the sphere through the center, which makes it a great circle. At the equator, turn east. Meridians meet the equator at right angles, so the first square marker belongs to the surface geometry. Move east for exactly 1/4 of the equator. The glowing arc records the turn while the starting meridian stays visible. At the second point, turn north. The equator meets this new meridian at another right angle, giving the route 2 certified corners. Pause before moving. If the traveler follows the shortest northbound surface path, will it miss the start or return exactly to it? Trace the second meridian north. Every frame stays on the same great circle, and the gap to the starting point steadily collapses. The route closes at the North Pole. 2 right-angle turns have carried the traveler back to the original point from another direction. A triangle needs an angle at the pole too. Perspective hides it because both meridians seem to lean across the curved globe. Rotate the globe without changing the route. From above, the 2 meridians separate into radial lines whose angle can be read directly. The radial lines are perpendicular. The third angle is 90 degrees, completing the same 270-degree payoff from the opening. Place a flat triangle beside it. Both figures have 3 sides, yet their angle totals disagree because their sides live in different geometries. That comparison creates a sharper objection. The spherical sides look curved on screen, so why are we allowed to call them straight? A literal straight chord between 2 surface points cuts through the sphere. It is shorter, but it leaves the world where the traveler lives. Constrain every candidate path to the surface. The relevant question becomes, which surface path requires no continuous steering and has least length? One candidate follows a small circle of latitude. It looks level on a globe, but its circle does not pass through the sphere's center. Move a traveler around that latitude. Its forward arrow must keep turning toward the pole, revealing continuous steering even at constant speed. Now move the same traveler along a great circle. Within the surface, the forward direction carries itself without that sideways correction. Imagine both routes as elastic bands constrained to the sphere. Which one can settle without sliding sideways, the latitude or the great circle? Release them. The latitude band slides toward a great circle, while the centered great circle band stays exactly where it was placed. This locally unturning surface path is called a geodesic. On a sphere, geodesics are arcs of great circles. Between ordinary non-antipodal points, the shorter great circle arc is the shortest surface route. That is the precise claim our triangle needs. At exactly opposite points, infinitely many half-great circles tie. Straightness survives, but the shortest route is no longer unique. Return to the opening triangle. Each side belongs to a great circle, so every side passes the same geodesic test. With straightness settled, hold the sphere and both equator squares fixed. Move only the gap between the 2 meridians. No matter where the second meridian moves, both meridians still meet the equator at right angles. Those 2 corners remain fixed at 90. The pole angle is the longitude gap itself. Call the already visible gap theta only after watching it physically open and close. Start from 90 degrees, then predict the total when the pole gap is cut in half while the other corners stay square. Move the meridian onto the target. 90 plus 90 plus 45 gives 225 degrees, still above the flat total. Shrink the gap to 15 degrees. The total falls to 195, approaching 180 without ever reaching it at positive area. Now open the meridians to 120 degrees. The total grows to 300, and the enclosed surface patch grows with it. For this family, the total is 180 degrees plus theta. The amount above flat is exactly the visible pole angle. Watch the colored patch and the excess meter together. When one doubles, the other doubles across this entire controlled family. Keep all 3 angles fixed and enlarge the sphere. The triangle keeps its shape and angular coordinates, but its physical area grows. Double the radius and the patch becomes 4 times as large. Any exact area rule must therefore contain the radius squared. Return to the 3 right-angle triangle. Its excess is 90 degrees, and 8 identical copies appear able to tile the sphere. Before counting, decide whether the highlighted triangle covers 1/4, 1/6, or 1/8 of the sphere. Rotate the octants into place. Exactly 8 copies cover the surface with no gap, making the opening triangle 1/8 of the sphere. A sphere has area 4 pi times radius squared, so one octant has area pi times radius squared divided by 2. The same triangle's angle xs is 90 degrees, or pi divided by 2 radians. Multiplying by radius squared gives the identical area. One family and one octant are encouraging, but they do not prove the rule for an arbitrary spherical triangle. Take an arbitrary triangle whose sides are great circle arcs. Extend each side all the way around the sphere into a complete great circle. The two great circles meeting at angle A enclose a curved wedge called a spherical lune, repeated on the opposite side. Open that angle while holding the radius fixed. The lune occupies the same fraction of the sphere as its angle occupies of a full turn. A full turn has angle 2 pi. The antipodal pair associated with angle A therefore has area 4 radius squared times A. Repeat the construction for angles B and C. 3 differently colored double lunes now cover the sphere with controlled overlap. Most of the sphere lies in exactly one colored double lune. Only the target triangle and its antipod receive extra coverage. Subtract one complete sphere from the 3 double lunes. How many copies of the target triangle's area remain in the coverage count? The target triangle and its antipod were each counted 3 times instead of once. Together, the excess coverage equals 4 triangle areas. The 3 double lune areas equal 1 sphere plus 4 triangle areas. Every term now points to a region already visible. Cancel 4 radius squared from both sides. What remains is the angle sum minus pi, multiplied by radius squared. The exact theorem is now earned. Triangle area equals radius squared times a plus b plus c minus pi. For 3 right angles, the excess is pi divided by 2. The rule returns pi radius squared divided by 2, exactly 1 octant. The angles did not merely break 180. Their excess recorded how much positively curved surface the geodesic triangle enclosed. The same geometry explains a familiar visual puzzle. The shortest route on a globe can look curved when transferred to a flat map. Choose 2 mid-latitude endpoints and lock them to the globe. The green great circle arc between them is the surface shortest route. Hold the route and both endpoints fixed. When the latitude-longitude grid becomes a rectangle, will the route still look straight? Unfold the spherical grid toward a flat rectangle. Every root point keeps its longitude and latitude coordinates throughout the transformation. On the rectangle, the route arches. Nothing about the journey changed. Only the representation of the curved surface changed. A flat map cannot preserve every global length, angle, area, and geodesic shape at once. Each projection makes a different compromise. A gnomic projection sends every great circle to a straight line, but it cannot display a complete hemisphere in one finite map. On a Mercator map, a straight line instead represents constant compass bearing. That rum line usually differs from the shortest great circle route. Project the opening spherical triangle onto the same rectangular grid. Its surface geodesic sides bend, but the route identity and vertices persist. A map can make the straight path look bent, and the bent constant bearing path look straight. The surface decides the geometry. That suggests a portable instrument. Instead of trusting the picture, let a geodesic triangle report the curvature through its angle error. Place the same meter on a plane. Every geodesic triangle totals pi radians, so angle sum minus pi reads exactly 0. Move it onto the sphere. The familiar triangle totals more than pi, so the signed angle error becomes positive. For a clean negative curvature comparison, use the Poincare disk. Every point lies inside a circle, and model geodesics have a strict construction. Inside the disk, a geodesic is a diameter or a circular arc meeting the boundary at right angles. Ordinary Euclidean chords are not the lines. The plane gave exactly 180, and the sphere gave more. Will the disk triangle give more, equal, or less? Because this disk model preserves angles, read each corner from the tangents to its 2 geodesic arcs at their intersection. The 3 measured angles total less than 180 degrees. Negative curvature produces an angle defect instead of spherical excess. Now place the 3 spaces together. Sphere positive, plane 0, and Poincare disk negative under the same signed meter. On each constant curvature surface, enlarge the triangle. The signed angle error grows in magnitude with the enclosed area. Shrink them. Every sufficiently small triangle approaches 180 degrees, because a tiny neighborhood of a smooth surface looks almost planar. For a geodesic triangle, signed angle error equals the integral of Gaussian curvature over its interior. Dividing by area gives the average curvature. The original 3 right-angle triangle was not an exception to geometry. It was a large, unmistakable positive curvature measurement. 180 degrees is not the universal definition of a triangle. It is the 0 reading for a flat supporting geometry. If geodesic angles total more than 180, the enclosed region has positive integrated curvature, as on the sphere. If the total is less, the region has negative integrated curvature, as represented by the Poincare disk triangle. The flat map never changed the route's geometry. It changed only how the supporting surface was represented on screen. The portable rule is simple. Build geodesic sides, measure the three corners, then compare their sum with 180 degrees. The surface decides what straight means, and the triangle reports the curvature. On a changing surface, the same meter reads the average inside.